Nuclear chemistry. Let's review concepts that we learned early on. The atomic number is the number of protons in the nucleus. The mass number is the number of protons plus the number of neutrons. We use X as the element symbol, Z as the atomic number, and A as the mass number. A proton would have an A of 1 and a Z of 1. A neutron would have an A of 1, a Z of 0. An electron, we sometimes use the symbol beta, has a mass number of 0 and an atomic number of -1. Positron, 0 and +1. And a helium or alpha particle, helium nucleus or alpha particle, has an A of 4 and a Z of 2. Let's look at radioactivity. Henri Becquerel in 1896 observed the decay of the reaction of potassium uranyl sulfate. Here we have uranium-92-238 decaying into thorium-90-234 and helium-24. That's emission of an alpha particle. Marie Curie in 1898 isolates polonium, another radioactive material. When you balance nuclear equations, you have to conserve the mass number. That is, in this case, uranium-92-235 plus a neutron decomposing into cesium-55-138, rubidium-3796, and 2 neutrons. The top numbers, 235 plus 1, of the reactants must equal the 138 plus 96 plus 2 times 1 of the products. You also have to conserve the nuclear charge, the atomic number. And this is the bottom row. 92 plus 0 equals 55 plus 37 plus 2 times 0. Nuclear stability. Certain numbers of neutrons and protons are extra stable. If a neutron or a proton number is 2, 8, 20, 50, 82, or 126, these isotopes are extra stable. These numbers are actually referred to as magic numbers. Nuclei with even numbers of both protons and neutrons are more stable than those with odd numbers of neutrons and protons. All isotopes of elements with atomic numbers higher than 83 are radioactive. All isotopes of technetium and promethium are radioactive. Here's a table showing the number of stable isotopes with even and odd numbers of protons and neutrons. Nuclear stability and radioactive decay. Let's look at beta decay. Here carbon beta decays into nitrogen, potassium into calcium. What's happening is a neutron is being converted to a proton plus an electron, a beta particle. There's also positron decay. Carbon is being converted into boron plus a positron. Potassium into argon plus a positron. Here the proton is being changed into a neutron plus a positron. There's also electron capture decay. A low-lying electron is captured by the argon nucleus, converting it into chlorine. Iron can do the same thing, converting itself into manganese. Here what is happening is a proton in the nucleus is being converted into a neutron by reaction with an electron. Alpha decay involves helium nuclei. Here polonium decays into lead with the emission of an alpha nucleus, an alpha particle. There's also spontaneous fission, where a radioactive nucleus breaks apart. Here californium 98-252 disintegrates into indium 49-125 plus neutrons. Now we're going to look at mass-energy relationships. Famous Einstein equation, E equals mc squared. Einstein realized that the mass of a particle is related to its speed. For a nuclear reaction, this change in energy is what we're interested in. Small mass changes are accompanied by large energy changes. There's a term called the nuclear binding energy. It's the energy required to break up a nucleus into its component protons and neutrons. So if we have fluorine 919, there's a certain amount of binding energy holding that nucleus together. We're going to calculate what it would take to break it into 9 protons and 10 neutrons. Delta E equals delta M times C squared. Delta M is 9 times the proton mass plus 10 times the neutron mass minus the mass of the isotope fluorine 19. To do these calculations, you need a table of isotopic masses, not the periodic table. Here are the values. The change in mass turns out to be 0.1587 AMUs. We can convert that to kilograms by dividing by Avogadro's number, and it becomes 2.635 times 10 to the minus 28 kilograms. If we multiply that kilogram mass by the speed of light squared, we get a change in energy of 2.37 times 10 to the minus 11 joules. Remember that this is for one atom. If we then multiply by Avogadro's number to get a mole, it becomes a negative 1.43 times 10 to the 13th joules per mole, or 1.43 times 10 to the 10th kilojoules per mole, which is a very large amount of energy. The nuclear binding energy is that 1.43 times 10 to the 10th kilojoules per mole. If we divide by the number of nucleons, the number becomes 2.37 times 10 to the minus 11 joules divided by 19 nucleons. We get 1.25 times 10 to the minus 12 joules per nucleon. Here is a graph that shows the nuclear binding energy per nucleon versus the mass number. Notice that it sort of peaks out at around iron 56 and then slowly drops down a little bit to uranium 238.